All right, so we talk about block cipher. So let me give a concrete example by talking about present. So this is one of the earliest lightweight designs we have. So for a very long time, it is ISO standard for lightweight cryptography. So this design is really simple. We have this 64-bit block size. So plain text here represented by lines. Each line represents a single bit. There are 64 lines here. So you either choose your secret key length as 80 bits or 128 bits. But actually, with many GPUs, you can perform a brute force attack on this key length. So I don't recommend it. I mean, if you need security for a few seconds, then maybe you can use it. But for long-term security, you cannot use it. All right, so regardless of your key length, you feed it into the key schedule algorithm, and it produces you 32 round keys. You have 31 rounds, but at the end we will add another key XOR. So this is why we have 32 round keys. So your single round is as follows. You XOR your input with the secret key. So this is your key addition layer. Then perform the SBox operation 16 times in parallel. And the SBox is provided here. We will analyze it for differential cryptanalysis soon. So this is not just randomly selected SBox, okay? This mapping is deliberately chosen in this way. It is one of the nice SBox 4x4 SBoxes. So here's an example. For instance, 1 goes to 5 in hexadecimal notation. So this means that if your input is 0001, output is 0101. So this creates the confusion. Then we switch the bits of the places of the bits, sorry. This is your permutation layer. And it takes time to implement it on software, but at the hardware level, this is very fast. Okay. So you repeat this picture 31 times. And at the last picture, you add another round key XOR here, and you obtain the ciphertext block. So let me talk about key schedule first. So if you use the 80-bit key version, we store your master key K as 80 bits like this, okay? So think about this as an 80-bit register. You have it there. So your round keys are actually the leftmost 64 bits of this 80-bit register, okay? So your leftmost 64 bits are actually XORed with your plain text here. Now, I modify this 80-bit register to create the next round key. What I do is as follows. I update this 80-bit register as follows. As you can see, here I represented with K0 to K79. Now it starts with 19. Here actually is a different way of saying that I'm rotating this 80 bits 19 bits to the right, okay? Then I applied the same SBox only to leftmost 4 bits. I write the results there. Sorry. Then I add a round key to this 5 bits. Round key means as follows. If this is your first round, you XOR it with 1. If it is the 30th round, you XOR it with 30. We added to 5 rounds because, if you represent 31 in the hexadecimal notation, it becomes, sorry, in the binary notation, it becomes 5 ones, right? So this is why it affects this. So some people didn't understand it in my previous videos, so I still get comments at YouTube saying that, can you explain this a little bit more clearer? So this is the picture for that, okay? So this is the 80-bit register representing bits from 0 to 79. So this leftmost 64 bits is my round key at the ith round, okay? So in order to produce round key of I plus 1, I perform these operations, and in the picture it appears like this. So I take this part, this 19 bits, as you can see, comes and goes here. And the other part actually comes and goes here. This is actually the 19-bit rotation to the right. Here, as you can see, there's an SBox operation. So I perform this SBox operation to leftmost 4 bits here. Then I add the round counter, to this 5 bits. And that's it, as simple as that. Not a big mystery here. But if you use a 128-bit key, the key schedule adds just one more S-box operation here. And your rotation now, rotating the 128-bit key to 67 bits to the right. That is the only difference. Okay. Also, of course, you are adding the round counter to these 5 bits. That's it. So as you can see, moving from 80-bit key to 128-bit key doesn't cause you a visible slowdown, right? Because you only have one more S-box, which is not that much of a problem considering the whole encryption process. But the thing is that you might then ask, why do we have the 8-bit version? For very small devices, which have very small amount of memory, storing 80 bits and storing a 128-bit is, sometimes causes a problem, because here you need like 6 more bytes to store. Okay, so it becomes a little bit more costly. So if you want to store just 6 bytes less, you have to move to here, this one. Okay, but again, this only it should be needed in very rare scenarios, so I always advise to use 120. When we talk about generic attacks, I will show you how long it takes to break present 80 when you have millions of GPUs. Okay. So let's give an example here. So here I want to show you how the key schedule algorithm works when you use the 80-bit key scheduling algorithm. So if you choose your 80-bit key as all zeros, this is in hexadecimal notation, so this is why there are 20 zeros here. All of the zeros in bit notation are 4 zeros. So recall that we take the leftmost 64-bit as our first round key, right? So this means that it is all zeros, right? Because the whole thing is all zeros. Then what we do is as follows: rotate this to 19 bits to the right, this whole 80-bit mass register 19 bits to the right. Nothing changes. It is still all zero. Then what we do is as follows: perform S-box operation to the leftmost 4 bits. And recall that when 0 enters the S-box, the output is C. Then you add a round counter to here, which actually doesn't affect the first leftmost 64-bit. So this is why your second round key is just C and this. Again, you rotated 19 bits, perform the S-box operation at the round key. So as you can see, S-box operation now gives you this. These are coming from round key XORs and so on and so forth. If you continue this way, you can see that the confusion and diffusion here is not that good, because I started with all zeros and I see a lot of zeros still, as you can see, right? This is actually why we call it a lightweight design. In a better design, you wouldn't observe this. For instance, look at AES, take all zeros. In just 1 or 2 runs later, those zeros will be turned into something else. Okay. Here, it takes like more than 10 runs to get rid of all of those zeros. Okay. So as you can see, designing something that has a good confusion and diffusion is not a good idea. Of course, here we are talking about the key schedule. Now let's look at the confusion and diffusion of the cipher itself. So assume that this is our key schedule. Now I use this key, so this key schedule, to encrypt the plain text, again all zeros. So this is block size of 64 bits. My secret key, assume that it is 80-bit zeros. After the first round, the output is, I think 8 Fs and 8 zeros. Let's go back to picture and why this happens. See why this happens, okay? So let's go to the present picture. Right? I start with all zeros. I XOR with the first round key, which is again all zeros. So nothing changes, it is all zeros. So all of the 16 S boxes have the input 0, the output is C. So we have 1, 1 zeros, 1, 1 0, 1, 1 0 here. But the permutation designed so that rightmost 2 bits actually kept on the right part of the cipher, but leftmost 2 bits of the output of the S-box are sent to the, if you divide the cipher from in the middle, these 2 bits are sent to the left part. So all of the ones are sent to the left part, all of the zeros are sent to the right part. This is why we have 32 ones here and 32 zeros here. Of course, in the hexadecimal notation, it turns into Fs and zeros. Perform one more round of encryption. The output is this. Again, as you can see, it is not. This is why we don't design the present cipher as 2 runs. As you can see, it doesn't have enough confusion and diffusion. Okay. If you continue this way, you will realize that the confusion and diffusion is a little bit better than the key schedule. Now we have random looking values, right? If you continue this way, this is your 31st output, and you also XOR it with the final round key, and this is your ciphertext block. So this is important because this is your actual test vector, okay? So if you want to implement present, just implement it and check if you see, of course, first check if the key schedule values match my values, and also then check if these values matches mine. It is hard to implement a cipher correctly in your first trial. So this is a very nice example. So, you know, this can be used to check if the cipher, you know, if you implement it correctly. But also you can see that the cipher designed to be 32 rounds because, you know, designers try to break it themselves. So they find attacks to like 10 rounds, 12 rounds, and so on. So since they can break those many rounds, they generally double it or triple it to design it so that when their attacks are improved by other people, they will not be able to break 31 rounds. Okay. So as you can see, this is not an academic approach. I mean, there's no mathematical formula to choose how many rounds you should design. Okay. So designers could say that we design it 32 rounds, but this would cause just a little bit slowdown, right? Because you will perform one more round of operation. They could reduce it to 30 rounds, but maybe some people would come up with an attack that would break 30 rounds. Okay. So there is no academic answer to tell you the exact number of rounds a cipher should be, because we are analyzing it against the methods that we know. But maybe tomorrow we will find another cryptanalysis technique and maybe break 30 rounds. So this is why they are trying to stay on the safe side by increasing the number of rounds, but not so much that it becomes very slow.